Hello, everyone. Today we have the pleasure of having Mr. Kidman present a paper on testing machine learning models.
Yes. Hopefully you all can hear me okay. Let me turn this thing on. Echo, echo, echo. Yes, yes, yes. Fantastic. All right. Well, thank you everyone for coming. Testing and quality of ML systems. That's what I'm going to be talking about. Just like they said, my name is Carlos Kidman. A few things about me really fast. I'm the head of engineering at an AI company right now. Before this, I was an engineering manager at Adobe around a organization called Automation and Productivity Engineering. We use machine learning there as well. I do lots of stuff with open source, including my own projects. The one I'm most known for is Pylenium, which is just a simple wrapper around Selenium and PyTest. I do lots of keynote speaking all over the world. This is my first PyCon, so yes, I'm so excited. Yay, PyCon. I also have I stream on Twitch once or twice a week, depending on how I feel, and then I have a YouTube channel. And my most exciting one, I feel, is that I'm the founder of QAP, or QA at the Point, which is the software testing and quality community here in Utah. So yes, Utah-based for anyone else. If you are a tester and you're in Utah, you should be part of this community because it's pretty amazing. So, going right into it, I feel like when it comes to software testing and quality in traditional software development, it's a pretty common topic. You have software testers, you have people that are in the testing space like SREs, stuff like that, right? But when it comes to machine learning and AI, it's as if it's a new field, it feels like. There's not a whole lot that happens in that space. And so this is what got me really interested in how do we monitor, how do we measure, how do we test and kind of measure the quality of these ML systems that we're building. And now that I've been in this space for about 5 years now and building these models, they've definitely gotten better from when we first started, even just 5 years ago, and some people have been doing it way longer than I have. But like I said, testing is relatively new to this space. So Tulsi and Jacqueline, back in 2019, they learned at Google that if they didn't do software testing early and often, they ran into a lot of problems once they deployed their models into production, once they deployed these systems. And so in their talk here at Google I/O, they talked about here's some of the things that we learned, here's some of the things that we do now, and we try to bring in software testing as early as possible. So to make sure that we're all on the same page, because I don't really know where everyone is at. You may be brand new to Python, you may be a machine learning engineer right now, I don't know. So we're going to go through a very simple exercise here with a very common machine learning application, which is prediction, right? And Jay Alamar said this really well. He said, prediction is predicting values based on patterns and other existing values. Once we understand this bit a little bit, it'll be like, wow, machine learning. So let's say that we are the machine learning engineers at this grocery store, and our job is to predict how much we think customers would spend when they come in, right? Let's say we have this as our data set. A group of one person comes in, they spend $10. Group of two, they spend 20. Group of four, they spend 40, right? So if I were to ask you, how much do you think 3 people will spend, what would you say? 30, right? How did you come up with the answer of 30? Yeah, because we're smart, Carlo. Yes, you found this magical number of 10, right? Which happens to be the relationship between the numbers in this table. So if you were to grab 3 and then multiply it by 10, well, very easily 30, right? If I said 7, you would say 70, on and on we go, right? And someone said regression, exactly, right? This is essentially how machine learning models work, right? And in this case, this is a supervised learning thing. But yes, it finds these relationships between the data, and that's what it outputs. Now, in the top here, this is the paradigm of traditional programming, where we define the rules, put in the data, and then we get answers right back out. So if we had let's say we had a function that was called like isEven, and you passed in the number 3, you'll have some rules in there to determine that is either true, it's even, or false, it's odd. So writing unit tests for that should be fairly simple, right? Assert that if I pass in 3, I get false. If I put in 2, I get true. Machine learning is a little bit different because here you input the answers and the data, and the machine learning algorithm determines what the rules are instead. So the output's going to be different. So what makes this difficult when it comes to software testing is the fact that it is not guaranteed that the group of 3 people are going to spend $30. They might spend 28. They might spend 50. They might walk in and then just go to the bathroom and then leave, right? They might not spend anything at all. So because of that, it's difficult to say, well, let me assert that 30 is the case. Instead, you have these rules that get outputted. You have these ranges, these boundaries. It's different than traditional programming. But in this case, there's different points of fault inside of a machine learning system, right? One of the big ones is obviously the data set. The data is what drives the entire machine learning system. And so if there's problems inside the data set, you're already going to have issues with what gets outputted. So software testing can happen really early and later as well. And that's kind of what we're going to be talking about today, is the testing and quality of these things. So in software testing, we have this concept called shift left. Does anyone want to take a stab at what shift left means? Move or higher up your data stack. I like that a lot. Anyone else? Do it earlier. I mean, the white text there kind of throws it off, right? But anyway, if you were to take the software development lifecycle, right, which is usually a circle diagram, and it's like step 1 is planning, step 2 is design, step 3 implemented, and you deploy and all the good stuff. If you were to take that circle and flatten it out, where step 1 is on the left, and the last step is on the right, when we talk about shift left, we're talking about trying to bring a lot of these quality and software testing practices as early in the process as we possibly can. In a lot of companies, they will do all of their development right in the middle, and usually you get requirements from UX or product or business. You build the thing, and then when you're ready to deploy, you give it to someone else. They deploy it, they observe it, they monitor it, they operate it, right? So shift left is talking about how can we include our software testers, our developers, as much of the team as we possibly can, as early in the process. Because the more you are there in the design of things, the better things will happen downstream. So let's say we take an example project that we're building, a new ML project, right? And let's kind of go through the process here so we can see what this will look like. So step 1 is we want to define the problem. What are we trying to solve? In the previous example with the grocery store, the problem was we want to predict how much people will spend. That's not a very good problem statement, though, because why are we wanting to do that? Right? It could be that for the grocery store, we care about preventing understocking or overstocking. Right? Especially with perishables like milk or dairy. If I buy too little of milk and then people come in expecting milk, well, now I'm losing money as a business because I don't have any milk for them. So we overstock, we buy tons of milk, but then we only sell half of our stock. So then the rest of my stock goes to waste, I lose all that money, it's also a problem. So it could be that we're using machine learning to help prevent the understocking and overstocking problem. A much better problem statement than can we tell how many people, or can we predict how much money is going to be spent by people? Moving on, who is the ML system for? Again, back in our example here, is this for the people doing stocking at night? Is this for the store manager? Is this for the VP of the region? Is this for who's going to be using this thing? It could be that the ML system is to feed another ML system, right? That could be the case as well. So who is the system ultimately for? And then, of course, does this even need machine learning? When I first started, you better believe I was like, wow, I know how to do a few little simple machine learning things. Can I apply to everything? And a lot of the time, the answer is yes, but sometimes you don't want to do that, right? With the is even, is odd, imagine applying machine learning to tell me if 3 is odd. Probably not the best example, right? So moving on, number 2 is define success and assess risk. Success, assess, man, English is hard. You want to start by defining initial baselines. And in doing this, let me go a few more right here. That creative proof of concept is one of the most underrated pieces that teams miss right now. Because it's so easy now to build these machine learning models, right, with things like transformers, for example, you can get to predicting things within a few lines of code. And so you might try those out and say, well, this is good enough to start just building things. When instead, if you build a proof of concept and actually start defining these baselines for what success looks like and what risks you want to avoid or mitigate or prevent, this is going to force you into building something that's a lot more practical rather than the shiny toy that is a transformer, let's say. We're dealing with a lot of data, so of course there's going to be privacy and security risks as well. Again, another piece that a lot of people don't think about. And then, of course, one of my favorite questions here is, do we even have the proper resources to do this? If we were building an ML system that was meant to detect cancer in patients, let's say, me, Carlos Kidman, am the worst possible person to tell you if this thing is working or not. So even though I may be a software tester by trade, I would suck at testing that system because I myself don't know how to detect cancer even manually, right? So do we have experts that can help in our team to make sure that we're building the right thing the right way that is actually helping, right? Another example would be like sentiment analysis. I'd probably want some linguists on my team, for example. So do we have the proper resources? Number 3 is design the initial architecture. Which database or tables are we going to pull data from? What does our ELT process look like? Is this going to be behind a REST service? Is it going to be on a mobile device? It might not have internet if that's the case, right? How are we going to monitor this? Monitor and measure it as we're developing it. What about when it's inside production? How are we going to monitor things as well? Yeah, I'll just keep going because of time. Number 4 is to collect data. Where's the data coming from? This is a little bit different than what I asked before in the databases because this might be our data is coming from recordings at a traffic camera. This could be we're recording user session data and that's being streamed in. The different sources you have will also determine how you do a lot of this as well. Is this different than staging your dev? Are you just grabbing things from production and cloning it into a stage database? Or are you doing some different filtering? How much of it is synthetic versus actual prod data? Where are we storing the data? Is the data being streamed or batched? Basically, at the end of the day, what I'm trying to get at is you got to understand the data journey that it's going through, right? It's not enough to just say, well, as the machine learning engineering team, I just know that Snowflake has all my data in these few tables. I don't need to know what happens before that. All I care about are my tables, and that's enough for me, right? Well, it's really hard to do software testing if you're oblivious to what's happening beforehand, right? So let's take a simple diagram here. This is a very simple ELT process. On the left, it starts there and then goes to the right. We have our sources coming from user sessions. So customers on a website, they're doing things, and kind of like Google Analytics, data is being streamed in, right? In this case, we're using Kinesis to stream the data in and loading it into S3. And we're using that as our data lake, let's say. Then from there, we have some DAGs that do transformations, and there's different transformations depending on where the data is going to eventually land. So for example, we have Neptune and Snowflake, and we're putting data in those places. As software testers, we care about every single one of these steps. Why? Because each one of these steps, there's going to be risk in each one of those. If Kinesis goes down for whatever reason, then everything downstream gets screwed. And so we want to make sure that we have not just testing and monitoring in place, but also fault-tolerant practices. If Kinesis were to hiccup, would we know about that? Would we be able to automatically get it back up and going again? That's all part of software quality, right? And so we care about these steps to make sure that once everything on the right-hand side over here, you can't see it, but this is probably where the machine learning stuff lives, right? That has the best data that it possibly can. But when we say, what's good data? Well, you have to define those things. You don't just get good data by writing these theoretical tests that I'm talking about, right? Number 5 is then preparing data. Now we're getting into actual like machine learning stuff, right? So now you're preparing data. What shapes does the data need to be in? What are the data types? Are there any missing values or errors? Basically, poop data makes poop models, right? And this is where a lot of our machine learning engineers, the AI, the data scientists, they're doing a lot of testing here already. So I'm going to go through this part pretty quick, but already lots of experimentation, lots of testing happens here. I have data analysts for things like this and data engineers because I am not the best. But yeah, we have these people because we know that this ML systems, the lifeblood is the data. So we want to have people, you may call them testers, but they may be data analysts in your HR tool, but they're still testing the data. Next up, we have training and validating models. So we experiment and compare models, capture training validation metrics, visualize results, tune weights and parameters, and hopefully using tests, exploratory and automated, to help you as you're doing this. In a previous team that I had, they would do all of their experiments all locally, and they would open like a new tab in VS Code and be like, here's the results. And then for the next run, they'd open a new tab, and okay, here's the new results. Very manual process. And nowadays we have companies and platforms that are building tools specifically to help you kind of track all of your experiments and test results. So hopefully you can use some automation as well to help out, to speed things up. And we'll have some examples here soon. So I think that here, let me see. Yep. So when I talk about validation, the reason why I call it that is because I want it to be a little bit different than what we refer to as testing. So validation is how well does the model perform against a data set it's never seen before. So even though, yes, you can call it testing as well, because it kind of is, right? You do like a test, training, split, and whatnot. I'm calling it validation just so that we don't overload the word test too much, because it's pretty overloaded. So you can think that during training, maybe our model has a 95% accuracy. Wow, so smart, so great. But then during validation, it's 76% accuracy. So some people would say, well, this looks like a great indication of overfitting because my model knows the training data really, really well. And yet I'm saying testing is a different thing than this as well. The only reason I have facial hair is so I can do this. So step number 7 is then testing the models. What behaviors does the model show? Does it demonstrate harmful biases? Does it meet those actual privacy and security requirements that we had? Is it performant and reliable? And performant in this case is, for example, can it handle a very large load of users using it at one time? Can it withstand things like adversarial attacks, which is now more about the robustness of the model than anything? Does it solve the problems that we set out to solve? So the understocking, overstocking, is it actually solving that problem or not? Or is it only doing a really good job of predicting how much people spend? And then, of course, do our customers enjoy using our ML system? Sometimes they may not even know that they're using it, right? That might be a good indication, who knows? But do they enjoy using it? A lot of people are wary of AI because, like, well, I don't want the machines to do everything, and they have, there's some truth in that. So you want to make sure that they can trust your system, they like using it, and they want to keep using it. Number 8 is then deploy the model. Again, is the model itself going to be behind a REST or GraphQL service? Is it going to be on a mobile device? Maybe an airplane or self-driving car. Maybe it's a model to tell you that you need to restock your fridge and here, buy some more eggs, you ran out. Or maybe it's supposed to give you diagnostic information about a turbine, right? Is it a serverless function, maybe feeding other things? For software testers, when we talk about like a REST or GraphQL service, well, there's lots of API testing techniques we can use, right? We can use the requests library in Python in order to make these requests and see that the responses we get back are good. If you think of performance, we can use Locust.io to do performance testing and see how many requests can my model handle at one time. Can it handle a million predictions within a second? Interesting questions that you ask in order to test and measure the quality of these things. And then step number 9, you observe and iterate. And this is, you monitor, measure, alert, insights, learn. This is, you're operating in production now. So big terms like observability, operability, these things come to mind when I think of this step 9. And if you're not sure what these terms mean, it's a great thing to note down, do some research afterward, because they're pretty awesome topics. All right, so through all those steps, what we're thinking about is how can we prevent risk? How can we mitigate risk? How can we detect risk or problems, right? When I think of prevent, that's where the shift left happens. It's not easy to prevent if I don't holistically know what my ecosystem is going to have, if I don't holistically know the problem we're trying to solve, how customers are going to end up actually using this thing. It's difficult to prevent problems, right? And so in software testing, we'll do things like risk storming, example mapping, and different collaborative techniques. So you've probably heard of like behavior-driven development in order to get the team on the same page as to what do we care about, what heuristics matter to us when it comes to this ML system we're building. Mitigation is, when I think of mitigation, I'm thinking of things like blue-green deployments, feature flags, A/B testing. How can we prevent or mitigate as much risk as possible? For example, going back to the cancer detection, I may want to just release my ML system to one doctor that's working with us closely to say, how is it working for you, and get some feedback from them. If things are working well, let me release it to the whole hospital now. Let me release it to then 5% of my customer base, then 50%, and so on and so forth, right? And then detection is where you'll have like test automation, because those kind of functional tests can detect problems and that kind of stuff. So lots of different techniques you can use when you're thinking about software testing and quality. So Zillow, this is a very common problem. Hopefully people have seen this before. Zillow is a real estate company, and they wanted to build an ML system back in, I want to say 2019 or 2020, that would allow them to automatically buy properties and then sell them at a higher price later on and make a bunch of money, right? They would hire hundreds of people in order to do all this analysis themselves, and so they thought, well, we don't need hundreds of people if our machine learning system can do this all on its own. Sounds fantastic, and at the beginning it worked really, really well. But then eventually it went down very fast, right? They actually had to let go. I want to say it was like 25 to 50% of their workforce they let go. Because, oh, there it is. Because there's a huge problem. And this person tweeted on the right-hand side saying, I sold my house to Zillow last week for $550,000. They called me to buy it back. I offered $350,000 and they accepted it on the spot. So within a week, they made $200,000 just because they took advantage of the ML system that Zillow had. So what do you think happened? Like, how could that possibly happen where things worked so well and then eventually things went obviously so bad? Anyone have any ideas? There's adversarial attacks. What was that over there? Yes. Whoa, yes. Lots of different things, right? And I would say every single one of you are absolutely right. There was. What was that? Sorry.
The engineering realm, the features.
Yeah, the feature engineering could have been off as well, and yes, that was definitely a huge part of it too. There was a lot of problems, so we'll go through this part really quick. But there was poor data quality. There was it was easy to game the system. They were entirely dependent on the ML system, so there was very little to no human intervention for this ML system. So it could automatically buy properties and sell them however it wanted to. Now, this was done before COVID as well, right? So when I say risk from external factors, once COVID hit and the market went crazy, instead of pausing the system going, well, let's take a second to step back, it stayed on. And so as the market changed, and it was trained on historical data when there was no COVID, all of a sudden there is COVID, and they didn't do anything about it. Goodness, lots of problems. So on the one that I took away from this was, it was good at first, and it got worse over time. And this is one of the big problems that we have, not just in machine learning, but in software development as well. You have a team of developers, they build something, deploy it, and then they immediately move on to the next task, because that's what they do. So it may have been great for the first 3 months. Oh, Carlos, we monitored for 3 months and everything looked great. It's time for us to move on to the next thing. And yet after 3 months, COVID happened and then things blew up. So this is where the concept of shift right comes into play. Who would have thought, right? Doesn't that make sense? Shift right. This is what happens post-deployment. And maybe during deployment too, but post-deployment. And so I mentioned SREs, or site reliability engineering. A lot of them live in the right. Because they care about what happens inside of production, and you have probably a team of people observing this and working with it. So I made this diagram, a really simple one, just so you can kind of see that instead of it being this linear thing that I talked about, right, it's meant to be this infinity loop. It's meant to be, and this is a diagram of ML ops, by the way, but it's meant to be, you continue to observe, you continue to iterate, and you don't stop. Right? There's going to be things that you're going to optimize in your data collection, optimize in your data preparation, optimize in your training, and probably retraining. If you're not doing these things, then you run the risk of things like data drift happening to your application, right? And then immediate biases like historical bias get introduced. So of course, MLOps requires good processes, testing, and automation. This is much easier said than done, of course. As is with anything that involves humans, it's pretty difficult to have something that's really robust that everyone feels great, But alas. So let's go right into testing techniques now, so then we can wrap it up with concrete things that you can take away. So the first one is adversarial attacks. This is you trying to exploit the model, trying to find its weaknesses and take advantage of them, just like the person did with selling their house and then rebuying it. So on the left here, you see a turtle. And in this case, the ML system that's already been trained, deployed to production and everything, is identifying this turtle as a rifle. I think this is a rifle, Carlos. Well, it's funny, and yet at the same time, what are the potential implications or risks that happen because it thinks a turtle is a rifle? Hopefully no one's walking their turtle and then the SWAT team shows up and kicks their butt. On the right-hand side here, we have a stop sign. And in this case, the self-driving car saw this as a 45-mile-per-hour speed limit sign, just with a few stickers placed on top of it. Now again, this may seem like a really simple example, but that's not uncommon in the real world. There might be graffiti on the stop sign. If there's a graffiti on the stop sign and it doesn't see it as a stop sign anymore, you're probably going to kill someone. Interesting. Moving on, in this case, this is security AI. On the left-hand side, it detects a person very nicely. On the right-hand side, this person is completely invisible to the system. All because they're wearing a colorful little square. And I have, in my house right now, I have a security system like this that detects animals, right? There's a dog walking across your driveway. It can detect these things. So if people can be invisible to this ML system, security AI that I purchased, that I'm spending money for, they can just walk right into my house, no problem. Well, that's scary for me as a consumer, right? So become the attacker. I'm going to go through this really quick. It's not only for computer vision. Obviously, I'm showing computer vision because it's the one that you can see and look at. You don't have to be a data scientist or an analyst to create these attacks. You don't have to know how to code either. If you take my course on Test Automation University, that is called Intro to Testing Machine Learning Models, I actually show notebooks and code that you can use in order to do these kinds of attacks. Be a part of threat modeling. If you don't know what threat modeling is, that's another thing to write down and do some research afterward. And then, of course, be creative and design tests and attacks. Right? Sometimes you got to be creative to find these solutions, like us using the Earth as a satellite. That was pretty insane, right? Being creative with these kinds of things. All right, now for behavioral testing, this is us when I talked about testing behaviors and whatnot. This is what I'm talking about, behavioral testing. This is beyond accuracy in those lost metrics. You got to define those desired capabilities during design, right? So that's the shift left aspect of it. You can't just say, well, let's make sure that turtles don't look like rifles. That might not fit your context of what you're building, right? So you and your team have to decide, what are these capabilities we care about? What should it be able to do and what shouldn't it be able to do? If there's a problem with it, how are we going to raise that problem in an elegant way to our users, right? The second part, testing behaviors, gives a more accurate picture of model performance. And this team that actually wrote this white paper, they said that they created twice as many tests and found almost 3 times as many bugs because they were doing this collaborative design, that shift left approach, and then moving into development. So what does this look like in the real world? On the left-hand side, you can see the capabilities that they defined. One of them was vocabulary. If you can only have 5,000 tokens inside of your vocabulary, well, those 5,000 tokens better be high-quality words. For example, the word and, probably you don't want that in your vocabulary, right? The next one, NER, is named entity recognition, and then negation as well. Those are the rows. The columns they had were different testing types. You have the minimal functionality tests, invariance, and directional. We'll get into some examples of this. On the right-hand side, they have a table of test cases that they're going to be using to test these different capabilities. So you can see, like on the right-hand side, it says, I can't recommend the food. They expected it to be a negative sentiment, and yet the model returned it was a positive sentiment, so the test failed. Enough of these tests they had, and after all the tests executed, it had a failure rate of 76.4%. Why does this matter? Well, it matters because, and I'll go through this really quick. It matters because you're able to test multiple models at once very, very quickly. Now, I know this is a little hard to see. All of these rows here, these are all the capabilities. So you see like robustness and temporal, there's different capabilities here. But what I care about the most is this section here. This is the failure rate for all the models they're comparing. To zoom in on one of them, they have the failure rate for, there's a model from Microsoft, a model from Google, a model from Amazon, and then BERT and Roberta. The 2 tests they have here are the company's Australian. That should be neutral sentiment. This is a private aircraft. That should be neutral sentiment as well. And yet BERT had a really hard time determining this. And these were all state-of-the-art models. So again, past just the training and validation, there's more to be tested, right? These behaviors especially. Now, fair and responsible AI, this is testing for harmful biases. So in this case, if you look at, like, this is, in this paper, they were trying to show, here's data generation, and in here, all the red bits you see are different types of harmful biases. Zillow had the historical bias problem, where they trained the model on things before COVID, and then it sucked during COVID. Representation bias, measurement bias, and then as you're modeling and building things, even more biases everywhere, right? Problems all around. So fairness, when we talk about fairness, there's a few aspects. You can have fairness by data, fairness by measurement and modeling, and fairness by design. Let's go through some examples. Back in 2017, Google wanted to create an ML system that could detect toxicity online. This would be great for moderators in a chat room, maybe a video game or whatnot, right? So on the top, they had, if they put in I am straight, the model said this is 4% toxic, basically not toxic at all. But if you put in I am gay, the model said back this is 86% toxic, showing a harmful bias. So they decided, well, I wonder what other things has a harmful bias with our system. So they put I am gay, queer, Muslim, Jewish, Christian, straight, and notice the score of how toxic the machine learning system saw this as. Well, us changing just the token, that is an example of invariance testing. If I only change one word, does it change sentiment? How positive or negative, in this case, how toxic does this become? You can measure these things and do a lot of software testing against them. In this case, this is Google Translate. On the left-hand side, you have Turkish. Turkish doesn't have gender. For example, in Spanish, you do, right? Like you have la silla and things like that. When it translated to English, it automatically assumed that a nurse is she and doctor is he, showing a harmful bias, right? Another example, Casey is my friend. How do we know if Casey is male? How do we know if they're female, non-binary? We don't have that context. So by design, what they did instead was, how about we show them the different answers and the user can select the option that matches their context. So when I want to translate friend into Spanish, you get amigo or amiga, which one fits what you're trying to do. So to recap, we have the shift left, shift right, adversarial attacks, testing behaviors and the overall experience, testing awareness, harmful biases, and of course, hopefully this helps you get some ideas as to what you can search, different testing techniques you can use in order to test for these different things. And if you need help, software testers are here. You should leverage them because they can help you out. We need better testing all around in a very holistic way. So with that said, that's it. That's all I have for this presentation. I do have code examples for anyone that is interested in seeing how these tests can be written in a test automation format. But otherwise, I'm ready for questions, or I think we're actually close to time. So thank you.